All right, so this is, I guess I'm calling this 1.5 revisited. Oops. But we're also going to discuss a little bit of chapter P1, which was the Pythagorean theorem. So the deal is this week in 120, we're going to be talking about the law of sines and law of cosines. Sines, law of cosines in Math 120. And one of our applications, our main application, at least for this week, for these two laws, are going to be to solve triangles. And what I mean by that is, given information about a triangle, for example, if I give you 3 of the sides of a triangle, can you tell me the 3 angles, right, of that triangle? Or if I give you 2 of the sides and 1 angle, can you tell me what the third side is and what those 2 other angles are? All right, we'll obviously talk about that more in detail in Math 120, but that is what we're going to be doing, solving triangles, at least with at least as our main application for this week. So what I want to do is talk a little bit about what we already know about solving triangles, and that is in the context of right triangles, right? So at this moment, we can solve right triangles. Before understanding the law of sines and cosines, we know how to solve some triangles, and that is the right triangles, right? So for example, if I told you I had a right triangle like this, and I told you this angle here was 30 degrees, and I told you that side right there was 2, right? Then you could tell me all the rest of the information about the triangle. In other words, the last angle right there, right? And this side right there, and that side right there. Okay, and the reason we can do this is essentially because this is a right triangle, right? So it's super important that this is a right triangle, and that we have the Pythagorean theorem, and we know the trig functions, right? So for example here, I could say, for example, cosine of 30 degrees is equal to adjacent over hypotenuse. So it's equal to 2 over, and I guess I should give names for this. Let me call this C. Let me call this B. All right. And let me call this angle here theta. So 2 over C, right? And the idea here is we want to find theta, C, and B, right? Again, given certain information about a triangle, we want to find the rest of the information. Okay, so this tells me C equals 2 over cosine 30 degrees, right? Oh, by the way, we're going to be using degrees in this section pretty much exclusively, just because the book does it. If you look at, for example, all the online homework or the book's problems, they're all in degrees. So just to keep a little bit of consistency, I'm going to, instead of using radians this week, I'm going to kind of restrict myself to degrees. But of course, you do everything in radians just the same, because of course, degrees and radians are the same. Okay, or just different, let me say it like this, different measures of the same thing. Okay, so 2 over cosine 30 degrees, we know that, right? Cosine 30 degrees is root 3 over 2. And so ultimately, this is going to be 4 over root 3, right? And you can rationalize that and kind of fix it up, make it look a little nicer. But essentially, the point here is that we actually know what C is at this point, right? In the same way, we can figure out B, right? Because tangent 30 degrees is equal to B over 2. And that will give us B. B equals whatever, right? No problem. Okay, so again, this is revisited. We did this same stuff in 1.5. So I'm going to kind of go over this stuff relatively quickly and without too much detail. Okay, so at this point, right, we know B, we know C. What is theta? Well, theta is actually the easiest of them because we know that the total number of degrees in a triangle is 180. We have a right triangle, and so theta plus 30 degrees plus 90 degrees should be equal to 180 degrees, right? And so that tells me theta is equal to 60 degrees. Okay, just solving that algebra. Okay, so the point again is that when we have a right triangle, solving this idea of solving triangles is really, really easy. Okay, let me give another example. Let's say we have, again, a right triangle, but instead of, in this example, I gave you one angle and one side. Instead, I gave you two sides, right? Let's say I said this was 2 and this one was 5 here, right? So again, the question is, what's the rest of the information about this triangle, right? What is that angle? What is that angle? What is that side right there? Okay. Well, again, because this is a right triangle, this is fairly straightforward. For example, we have the Pythagorean theorem, which tells me that this question mark, I'm not even going to give it a name, I'm just going to call it question mark squared plus 2 squared is equal to 5 squared, right? And so question mark squared is equal to 5 squared minus 2 squared, which is 25 minus 4, which is 21. And so question mark is equal to plus or minus square root 21. But we know we're talking about physical triangles here, so you can't have a triangle with negative length. So we only keep the plus root 21. Okay. All right. And so we have our third side. Again, this was because of the Pythagorean theorem. And let me emphasize that. Pythagorean theorem. Okay. So that's actually going to be the primary thing that we really want to learn today that's new. Okay. We'll talk about that in just a couple minutes. All right. Once we have that, well, the angles are also no problem because we have our trig functions, right? So this angle right there, cosine of this angle, I guess I should give it a name, alpha, is equal to adjacent over hypotenuse. Oh, no. Sorry. Adjacent over hypotenuse, right? And so using arc cosine, I immediately have alpha, right? Equals arc cosine of 2 over 5. Okay, it might not be easy to compute arc cosine of 2 over 5, but the point is it's computable, right? And so therefore we do know that side. And this opposite side over there, we can get it just as easily, right? Using the fact that sine of beta is equal to opposite over hypotenuse, right? Or once we figured out alpha, right, and we know this guy's 90 degrees, then we know that beta is 180 degrees minus alpha minus 90 degrees. Okay, so either way, probably actually the latter way, once you figured out alpha, you've got beta from the fact that triangles have 180 degrees total, is maybe a little better because, you know, calculating arc sine is not an easy thing, right? Okay, so ultimately, right, again, we can solve this triangle fairly easily because we know it's a right triangle and because we have, in this example, access to the Pythagorean theorem. All right, so my emphasis here is that Math 92 is really easy this week because it's about right triangles and it's about solving right triangles. Whereas Math 120 is going to be really hard because in Math 120, we're not going to be using right triangles. And so we're still going to be asking pretty much the same questions, right? Given two sides and an angle, what is the rest of the information, right? Exactly what we just did here. But in Math 120, we're not going to be talking about right triangles. And so we're going to talk about any random triangles, right? It might not be a right triangle. And so it's much, much harder. Okay, so the emphasis here is that because we have right triangles in Math 92, it's easy. Because we don't have right triangles, we have any random triangles in Math 120 this week, it's going to be really hard. All right. Okay, so one of the things that makes Math 92 easy this week is because we have this Pythagorean theorem. And what I really wanted to use this week for was to actually give a proof of the Pythagorean theorem, give you an explanation for why it's true. And actually, what that's going to do for our class is that everything we've talked about and everything we will talk about ultimately, in a way, depends on the Pythagorean theorem. All our formulas and stuff like that depend on the Pythagorean theorem. So if I justify the Pythagorean theorem, then everything in our class is ultimately justified, right? We can explain every formula, every equation, every algorithm in our class, and we will do that, right? We've explained all the formulas we've talked about in our class, except for that cosine alpha plus beta formula, but we will explain that in the future, right? And ultimately, all of it boils down to the Pythagorean theorem. So now, when I explain Pythagorean theorem, it actually completely explains everything in our class, all right? So there really is nothing that isn't justified, okay? All right, so let's give a proof of the Pythagorean theorem. So actually, there's many different proofs of the Pythagorean theorem. It's been around for thousands of years. The Greeks talked about it thousands of years ago. So there's a lot of proofs. There's a lot of really nice picture proofs. If you look, for example, on Wikipedia, you'll find a lot of very nice looking picture proofs where you're kind of just rearranging the triangles and rectangles and stuff to see that the Pythagorean theorem is true. But I'm going to give a proof that's more algebraic, just because it's really hard to reorganize pictures, on a computer screen like this. So I'm going to give an algebraic proof, which is really nice also because it only depends on understanding similar triangles. All right. So here it is. So what's the Pythagorean theorem? What we're trying to show right now is that if I have a right triangle right there, A, B, C right there, right? Then so we want A squared plus B squared equals C squared, right? We want to justify the Pythagorean theorem. I want to show you why it's true, okay? And again, the fact that this is a right triangle is 100% critical because this theorem is absolutely false if it's not a right triangle, all right? And in fact, one of the things we're going to talk about in Math 120, the law of cosines, is an extension of the Pythagorean theorem, or at least you can think of it as an extension of the Pythagorean theorem in the situation where you don't have a right triangle, okay? So heavily, I want to emphasize that, that the Pythagorean theorem only works if you have a right triangle. Okay, so this is what we want to show. How are we going to actually figure this out? Well, there's one small trick, and we'll kind of actually see this trick in Math 120 for general triangles in a way. We'll use a similar trick, but here's what I'm going to do. So here's my triangle. I'm going to drop this perpendicular from here down all the way to there. Okay, so what that does is it creates for me actually two more triangles, right? So I have my original big triangle, ABC, but I also have this triangle here from here to there, right? And I also have another triangle from here to there to there. Okay, so I have two more triangles to work with. And what's important is that those two triangles are both similar to my original big triangle, right? Similar in the geometry sense. So what I mean by that is, let me draw, for example, this small triangle in the corner here by itself. So it looks like this. There's the right angle. There's A. Okay. Let me draw this arrow like that. Okay. Now the deal is this, our big triangle over here. Let me just denote it like this. This angle right there, right, on our big triangle is shared with the small triangle that we're looking at right now, right? So when I draw this small triangle here by itself, that angle right there is the same as that angle right there. Okay, actually they're literally the same angle. Okay. All right. So what we have is that our big triangle up here is similar to the small triangle here because they share two angles in common, which means they share the third angle in common as well, right? Because the angle, if you have two triangles that share two of the angles, because the third angle is always 180 degrees minus the other two, right? the third angle has to be the same. So this angle here has to be the same as that angle as well. Okay, so these two guys are similar triangles. And what's important about similar triangles is that their lengths have this proportionality property, right? So let me use that. So that's actually the critical portion of this proof here. So what I'm going to do is I'm going to give this segment here a name. I'm going to call it C1. I'm going to give this segment a name, C2. All right, we were not going to be using C2 just yet. But the important thing is C1 is actually this length right here on the little triangle, right? And on the little triangle, notice that A is the hypotenuse, all right? Okay, now because these this little triangle and our original big triangle, again, I'm using this picture up here just to have it not be as messy. Because they're similar, we have this proportionality property, which says that the sides opposite each particular angle have to be proportional. So, for example, the side opposite of the right angle, right? So the hypotenuse of both of them. So hypotenuse of this small triangle, A, over hypotenuse of the big triangle, C, has to be equal to the length C1 on the small triangle over the corresponding length on the big triangle, right? Now, how do I identify that? C1 is the one that's opposite the angle with the double lines. So over here on the big triangle, A is the length that's opposite the double lines. All right. So C1 should be compared with A. All right. So we have this proportionality equation that relates the sides of the small triangle and the big triangle. Okay. All right, now this proportionality, this kind of property of similar triangles makes sense because if you kind of put these two similar triangles, you can always put them together so that they kind of look like this. So one of them is actually the other kind of expanded or shrunken, right? And then from there, you can see that each of these ratios, this over that, compared to this over that, are all the same, or this over that, right? Because essentially, two triangles are similar if one is the other triangle, again, either stretched or shrunken, okay? All right, so this proportionality equation, I can rewrite it as just cleaning up, right? Multiplying A on both sides, I get A squared. And then multiplying C on both sides, I get C1 times C. Okay, that's what we're going to be using. All right, we'll hold on to that for a second. And instead, let's move now to the other small right triangle, which is the one up here, right? Let me redraw that one. That one looks like this, right? Let's see. B is the common length, right there. And they also share a common angle, which is this double angle here, or denoted as with double lines. Okay, I don't even need to bother to give names for them. Okay, so again, my big triangle has an angle with this kind of double angle here, double striped angle, and a right angle. And my small triangle has this double striped angle, the same angle, and right angle. And so these two guys are also similar, right? So this third side is the single stripe. Okay. All right. And so the small triangle, the big triangle, again, are similar. And again, we have a proportionality property. This time, this length up here is C2, right? It's exactly this length right there. Okay. And so again, we can compare. Let's see. If we compare the hypotenuses, the small hypotenuse is B, right? Because that's the one opposite the right triangle. The big hypotenuse up here is, again, C. So B over C should be equal to, and again, let's compare the side. This time, let's compare the side opposite the single striped angle. That would be C2 for the small triangle. For the big triangle, the one opposite the single stripe is B, right? So the one opposite the single stripe is B, right? So we have B over C should be equal to C2 over B, right? And again, let me simplify this just by kind of getting rid of the fractions, multiplying B on both sides, I get B squared equals, and then multiply C on both sides, C2 times C. Okay, so this is the identity that we want to use for our second triangle. All right, I'm just now going to add the two identities together. So this one here from small triangle, the first small triangle, and this one from the second small triangle, I'm just going to add them, right? I'm going to add both the equations. So I'm going to get a squared plus b squared on the left-hand side, and then c1c plus c2c on the right-hand side. Okay. All right. The reason I want to do this is because a squared plus b squared is exactly the left-hand side of the Pythagorean theorem, which is what we want to confirm is true, right? What we want to verify. So what I would like is for the right-hand side to be c squared, right? If the right-hand side is c squared, then I'm done. That's the Pythagorean theorem, okay? But look at this. We've got c and c, so we can pull out that c, so c1 plus c2 times c, right? But what's c1 plus c2? Well, c1 plus c2 right here is just exactly c, right? Because I'm breaking up c into two pieces, c1 and c2. So their sum is just c. So this guy is actually just equal to c times c, which is c squared. Oops, c squared. And so ultimately, what do I conclude? By breaking up my big triangle into two smaller triangles, I conclude that a squared plus b squared is equal to c squared. Okay, so this verifies, this proves or verifies, I guess we're using the word verify in our class, verifies the Pythagorean theorem. Okay, so very, very simple idea, again, of just breaking up our big right triangle into two smaller right triangles and using the fact that we understand how similar triangles behave with respect to each other. In other words, that they have this proportionality property that, that you probably learned in high school or maybe even junior high trigonometry. Okay, so now we all know why the Pythagorean theorem is true. And again, the Pythagorean theorem leads us to many, many of the other formulas and equations in our class. And so now let's say at the end of our class, we will have justified every single formula and equation in our class from beginning to end. All right. Okay, so if you do look at the homework for Math 92 this week, it's going to be solving right triangles. And again, my entire point of doing these problems is that they're going to be really, really easy when you compare them to the problems in Math 120. And the emphasis, again, is that right triangles are really easy to deal with because we know we have a 90-degree angle there. Whereas regular triangles, Math 120, is going to be really, really hard. All right, so now you can move on to the Math 120 content and again, just compare how difficult the two classes are this week.